Hello, everyone. I'm Sedrick from Carnegie Mellon University, and today I'm going to share our paper, Pineapple, Personifying Inanimate Entities by Acquiring Parallel Personification Data for Learning Enhanced Generation. This paper was accepted to COLING 2022. To start, the main question that we're trying to solve with our paper is, how do we generate coherent, diverse, and interesting personifications? Now, for those of you who are not familiar, a personification is a type of figure of speech or figurative language where an inanimate object is being endowed with qualities that are distinctly animate and distinctly human. So an example is shown here at the right, where it says the freshly sliced pineapple serenaded my taste buds. Pineapple here is an inanimate object, and the verb serenaded is something that is distinctly human. So this is an example of a personification. Now, personification generation and being able to process personifications is really important for dialogue systems, for us to be able to implement systems which can more effectively process non-literal text as well as generate non-literal text. And this is also very important for AI-assisted creative writing, and it helps people add more flavor to their text. However, generating personifications is a very non-trivial task. This has been done to some extent previously with similes and metaphors, but very little work has been done with personifications. And really, the key difference is that with personifications, we don't have a fixed structure. For example, for similes, it needs to have the word like or as. And for metaphors, it's very loosely defined. You're just comparing two different things. But for personifications, it specifically has the requirement that the topic must be something that's distinctly inanimate, and the action or the description must be something that's distinctly animate or distinctly human. And so this really requires the model to be able to understand and to be able to model the concept of animacy. So the task more specifically is, given a literal sentence, how do we convert this literal sentence into one that contains a personification? To do that, we need training data. And so we gather a training data, which we call PersonifCorp, or the PersonifCorp dataset, which has 511 diverse personifications. And there's two main sources that we gathered from. The first one is from ACL prior literature. The main one here is the Deja image captions dataset, which contains around 6,000 image captions, around 4% of which are figurative. And then we just filter out those figurative sentences and look for the personifications. And we also use Kaggle or SEM-eval tasks. There's a lot of datasets here, which contain figurative language. And so we can filter out those datasets and look specifically for personifications. And so using these two main sources, we then compile them and gather our PersonifCorp dataset. For our test set, we want these test sets to be very high quality examples. And so we ask some humans, we give them a list of personifications, and we ask them to generate a list of literal and personification pairs. And really, in order to train our model, we will need personification and literal training pairs. Because if we want to have a sequence-to-sequence task, we need the input to be the literal sentence and the output to be the personification. And that way, the model will be able to do this task more easily. So our main focus then shifts to this question here at the bottom, is given our data set of personifications, how do we generate this parallel corpus? How do we de-personify a sentence? Some examples are shown here in the table. In the first line, for example, it says how far that little candle throws its beams. Throws being something that's distinctly human. And after the de-personification pipeline, it becomes how far that little candle can spread its beams. Spread being something that both humans and non-humans can do. Here we see a diagram of our pipeline, of our de-personification pipeline, with the three main steps. These are topic attribute extraction, candidate generation, and candidate selection. In the next few slides, we'll be going through these one by one. Here, I'm just showing an example. So for example, we start with the sentence, "The stars dance playfully in the moonlit sky," which is a personification. Then we extract the topic and the attribute. We mask out the attribute. We generate candidates, and then we pick the best candidate for the de-personified sentence. So the first step in this process is topic attribute extraction. Now, what is the topic and what is the attribute here? These are actually terms that we defined in order to help us more easily understand and decompose personifications. And this was inspired by the topic vehicle decomposition that was previously used for similes, and we expanded to be topic attribute used for personifications. So we define the topic as a noun phrase that acts as a logical subject, and the attribute as the distinctly animate action or characteristic that is being ascribed to the topic. Here in the table on the right, we see that attributes can be many different types. It can be a noun, for example, the planet Earth is her mother, mother being an attribute that's a noun describing Earth. It can be a verb. For example, my alarm clock yells at me to get out of bed every morning. Yells being a verb, the attribute describing the topic of the alarm clock. And finally, the attribute can be an adjective. For example, Justice is blind and at times deaf. Blind and deaf being adjectives that are distinctly human, describing justice, which is something that's non-human. So the way we gather and extract these topics and attributes is with the use of dependency parse trees and iterative merging algorithms. So what this means is that we have these rules. So for example, for alarm clock, if we see that it's a compound noun, or for example, if we see a coordinating conjunction next to, for example, a verb, that's an example, then we can use these certain rules that we designed to merge them together, and we continue merging until finally we're left with a topic and an attribute, and that's what we use. Now that we've gathered the topics and the attributes, the next step would be to filter out all the animate topics and only keep the inanimate topics. Why do we want to filter out the animate topics? This is because here our main step is de-personification. If the topic is animate, then we cannot de-personify because it is not a personification. A personification requires an inanimate topic. Also, the way we extract these inanimate topics is we use Comet's concept net relations. Here, more specifically, we use the is-a concept net relation, and we feed the word person to it. And what we found is that if we replace the x here in is-a x comma person, and we replace it, for example, with something that's very human, like for example, like doctor, it's going to give a very high match score. And if you replace it with something that's very non-human, for example, door, then it's going to give a very low match score. And this gives us a proxy metric for animacy that we can use to determine which topics are animate, which topics are not animate. Once we've determined the inanimate topics, we then mask out the attributes and use pre-trained BART to generate the top k equals 10 candidates based on the context of the sentence. Also here in the example, we see the top k equals 10 candidates listed here. Finally, once we have the candidates, we want to select the best candidate for the de-personification. To define what's best, we have three metrics. Animacy, which is we want the output of the de-personification to not be a personification anymore, right? We don't want it to still be a personification. So we have to consider the animacy of the candidate. Next is fluency. Of course, we want it to make sense. And the third one is meaning preservation, which is we want the de-personified sentence to still contain this, roughly the same meaning as the original sentence. We don't want to change the meaning of the sentence too much. So using these three metrics, we design a composite scoring metric that we define here with S sub I, and then we simply select the candidate with the highest S sub I score, and we use that as our de-personified output. Now that we have gathered the pairs of personifications and de-personified literal outputs, we're ready to train. And this training, basically, we use the de-personified literal outputs as the inputs to train our model. And the target outputs will be the personifications. And more specifically, we use a BART model to do the sequence-to-sequence training. Now, for our experiments, we compare with two baselines, which are Comet and the baseline BART. So for Comet, here we don't really do any training. This baseline is basically adapting our de-personification pipeline, but this time to do personification generation. So we use the is-a and capable of relations to generate candidates, and we use the same scores to rank and select what's best. Baseline BART is very similar to Comet, except this time we use BART to generate the candidates instead of Comet. So for both of these, we don't really do any sequence-to-sequence training. And for the last one, Pineapple BART, this is our proposed model where we do sequence-to-sequence training using our de-personified data and our personifications from our dataset. Now for evaluation, we use both automatic and human evaluations. For automatic, we use Blue, BERT score, fluency, and animacy. I'll go through these in the next few slides. And for the human, we use personification, appropriateness, fluency, interestingness, and meaning preservation. So here are our results for automatic metrics. Now we measure along 4 dimensions. The first is Blue, and the second is BERT score. So these two are meaning preservation metrics. As mentioned earlier, we want the output personifications to still have roughly the same meaning as the input. Next is fluency. To measure this, we use the generation losses or the log perplexity using a GPT-2 model. Finally is animacy. We want our output personifications to actually be personifications. And to measure that, we need some metric for animacy. And to measure this, we use the capable of relations that we previously defined with the Comet model. Here we see the results in the table, the PA BART representing the Pineapple BART results, and we see that indeed it performs better than the Comet and the baseline BART models for Blue, BERT score, and animacy, which is very promising. Now for fluency, it's slightly worse than baseline BART, but this also makes sense because if you're generating a figurative sentence and you're generating a non-figurative sentence, then it's natural that the figurative sentence will be slightly lower in terms of fluency because literal sentences are generally just more fluent, at least in terms of GPT-2. Now, the true test will be human evaluations. We showed humans the outputs of each of the models, and we asked them to rate on a scale of 1 to 5. And they rated alongside 5 dimensions, which are listed here. The first one is personification. Is it a personification? To what degree is it a personification? The next is appropriateness. And this basically describes how high of a match is there between the topic and the attribute, right? For example, if you want to replace the stars twinkled, you can say the stars danced in the night sky, which would have a very high appropriateness as compared to something that is a personification, but it's not very appropriate. For example, like the stars ate, that's not very appropriate. Fluency is, as described earlier, we want it to make sense. Interestingness is, as the name suggests, how interesting is it? Is it a very dull personification? Is it something that has a lot of flavor? And finally, meaning preservation, as we discussed earlier, we want the output personification to have roughly the same meaning as the input. And once again, we see that for humans, Pineapple BART outperforms our baselines quite significantly, and this is very promising. And finally, here we have qualitative results. We show some examples generated by our model. And what I want to point out here, the first is that our model can capture cases where the attribute is a noun, a verb, and an adjective. So it can capture all these very diverse cases. And this is shown in the first 3 examples in our table. So in the first example, their phone yells out loud, yells being a verb. In the second example, in most horror settings, silence is a ghost being a noun. And finally, her relationships are very lonely, lonely being an adjective. Next thing I want to point out is that it can replace and generate multi-word phrases. And lastly, it can also replace multiple segments in a single sentence. This is seen in the last example, the last row. the sound clap loud enough to make your ear cry, clapped replacing hit Frank, and cry replacing curate. So through these examples, we see that our pineapple model is actually very general. It can do all these different interesting things. And that's the end of our presentation. We invite all of you to take a look at our paper, look through our dataset and code. The links can be found here. Thank you very much.